Right now, as you read this sentence, you are falling. You are not falling down, but out. Your entire galaxy, along with hundreds of thousands of neighboring galaxies, is hurtling through space at over 1.4 million miles per hour, pulled by forces you cannot see toward a destination you will never reach. You are being pulled through a hole in the universe, a cosmic desert 2 billion light-years wide. This is not a metaphor. This is not science fiction. Scientists confirmed this in 2013, and yet over a decade later, most of humanity is entirely unaware of our true predicament. We are residents of a vast, underdense bubble of space-time so enormous it defies our most fundamental theories of the cosmos. We live inside the KBC void, a region of the universe where matter is at least 20% thinner than it should be. This emptiness is not a passive feature of our cosmic neighborhood. It is an active, distorting lens that is warping our very measurements of reality. It is a cosmic bubble in every sense of the word. And what we are discovering from inside it is causing our entire understanding of the universe to collapse. From our compromised vantage point, the universe appears to be expanding faster here than it does everywhere else. This single, seemingly small discrepancy breaks the most fundamental equations of physics. It has created a deep and unbridgeable gap between what our theories predict and what our most powerful telescopes see. This gap is known as the Hubble tension, and it is the single greatest crisis in modern cosmology. The entire 20th century model of the cosmos, a model built on the foundational idea that our place in the universe is not special, is collapsing under the weight of this single, terrifying discovery. We are not typical. We are not in an average place. We are, it turns out, in one of the strangest and most statistically unlikely places in the entire observable universe. We will journey through the story of the discovery that shattered our cosmological model. We will explore the cosmic web, the breathtaking foam-like structure of the universe that reveals 90% of all space is hollow. We will pinpoint our exact bizarre location in this structure. And most importantly, we will reveal what it means to exist in the desolate cosmic outskirts, and how this location provides a single, elegant, and horrifying solution to the greatest paradox in science. If you are ready to see the universe as it truly is, and to understand why our model of reality is collapsing, hit that like button and subscribe. Prepare yourselves. We begin. Discovery of the Great Nothing. 3 astronomers were counting galaxies when they noticed something impossible. In 2013, this was not a glamorous or headline-grabbing task. It was the hard, meticulous work of cosmic cartography. Ryan Keenan, Amy Barger, and Lennox Cowie, a team of researchers at the University of Hawaii, were attempting to build the most accurate 3D map of our local universe ever created. They weren't looking for a void, a crisis, or a revolution. They were just trying to count the lights. You cannot map the universe by simply taking a picture. A photograph of the night sky, while beautiful, is a deeply misleading two-dimensional projection. Galaxies that appear to be neighbors, side by side in an image, might in reality be separated by billions of light years, one just happening to lie directly behind the other from our point of view. To build a true 3D map, you need to measure distance. Astronomers do this by measuring redshift. This is the most powerful tool in the cosmological toolkit. As the universe expands, it stretches the fabric of space itself. A photon of light, a particle of light, traveling through this expanding space is also stretched. Its wavelength gets elongated, shifting it toward the red end of the spectrum. This is not the same as the Doppler effect, which is about motion through space. This is cosmological redshift, a stretching of space. The farther a galaxy is from us, the longer its light has traveled through this expanding space, and the more red-shifted it becomes. By capturing the light from a distant galaxy, passing it through a spectrograph, a scientific prism, and analyzing its chemical barcode of absorption and emission lines, astronomers can see how much this entire barcode has been shifted. This z-value, or redshift, is a direct, robust measure of a galaxy's distance. Keenan, Barger, and Coe were compiling redshift data from multiple massive surveys, including the Two-Mass Redshift Survey and the Sloan Digital Sky Survey, or SDSS. They were painstakingly plotting the precise 3D locations of over 35,000 galaxies, creating a map that stretched across billions of light years. Their work was built upon a foundational idea that has underpinned all of modern cosmology, from Einstein to Hubble to today, the cosmological principle. This principle is the ultimate extension of the Copernican revolution, the final step in humanity's great demotion. First, we learned Earth was not the center of the solar system. Then we learned the Sun was not the center of the galaxy. Then we learned our galaxy was not the center of the universe. The cosmological principle is the final statement. There is no center. It states that the universe, when you zoom out far enough, on scales of a few 100 million light years, is homogeneous, the same in every location, and isotropic, the same in every direction. Our cosmic neighborhood should be, on average, identical to any other cosmic neighborhood. When the KBC team counted the galaxies in a given cosmic volume, they expected to find a number that was, more or less, the cosmic average. The numbers were wrong. Everywhere they looked, in every direction, out to a distance of hundreds of millions of light years, the galaxy count was low. It wasn't just a little low. It wasn't a minor statistical blip. It was 20% lower than the cosmic average. The data was painting a terrifyingly clear picture. Our Milky Way galaxy, our entire local group of galaxies, and even our entire supercluster of galaxies all sit inside a colossal bubble of emptiness. The pattern was not just a local gap. It stretched outward from our Milky Way in every direction they looked, forming a colossal sphere of cosmic emptiness. This was not a small expected void between galaxy clusters. This was a super void. The team calculated its scale. The radius was approximately 1 billion light years, making the entire void a staggering 2 billion light years across. The researchers, stunned, did what all good scientists do. They assumed they were wrong. This had to be an error. They triple-checked their data. They tried to find a systematic flaw, a bias in their telescopes, a miscalculation in their code. They cross-referenced their findings with other independent galaxy surveys. They examined the sky from different angles, using different types of standard candles and redshift measurement techniques to ensure they weren't being fooled by an observational error, a cloud of interstellar dust, or a flaw in their instruments. The result remained consistent. The void was real. This discovery, which they modestly named the KBC void, pushed the boundaries of known physics. In our standard model of cosmology, the universe forms from tiny quantum ripples in the moments after the Big Bang. Gravity then amplifies these ripples, pulling matter together. Denser regions become richer,
forming clusters and filaments. Underdense regions get emptier, forming voids. This is the normal process of structure formation. But the model, which is spectacularly successful in almost every other area, simply does not predict voids this large and this empty. Computer simulations of cosmic evolution, which run the universe's 13.8 billion-year history in a supercomputer, rarely produce a void of this magnitude. When they do, it is an exceptionally rare statistical fluke. How rare? Some scientists calculated the KBC void represents a 10 sigma deviation from the average density. In statistics, sigma measures how far a result is from the average on a bell curve. A 1 sigma event is common, like being slightly taller or shorter than average. A 3 sigma event is rare, like a 1 in 370 chance. A 5 sigma event is the gold standard for a discovery in physics, a 1 in 3.5 million chance. It's so rare that it's discovered and not a fluke. A 10 sigma deviation is not a number our brains can process. The odds are so vanishingly small, you would not expect to find a single such void in the entire observable universe. Yet here we are, living inside one. The implications began to cascade immediately. If we reside in such a statistically impossible, special location, does that bias every single measurement we make of the cosmos? When we point our telescopes at distant exploding stars to measure how fast the universe expands, are we seeing the true global average expansion rate? Or are we seeing a distorted local version? The void hypothesis offered a stunningly elegant and deeply unsettling answer to one of the biggest paradoxes in modern science, a crisis known as the Hubble tension. What is a void really? The physics of emptiness.
When astronomers call a region a void, they don't mean it's a perfect vacuum, a patch of absolute nothingness. They mean it contains far less matter than average. The void around us, the KBC void, has roughly 15 to 20% of the normal cosmic density. Picture it this way. If you take a representative cube of the average universe, a cube 100 million light-years on a side, you might find 10 large galaxy clusters in it. If you take the same sized cube from inside the KBC void, you might find only 1 or 2. The galaxies don't vanish completely. They become rare, scattered islands in an endless ocean of near nothingness. So what is in this 90% of the universe's volume? 1. Dark matter, the same invisible gravitational scaffolding that holds galaxies together, also exists in voids, just in a much more diffuse, less clumped form. 2. Dark energy. This is the big one. This mysterious, repulsive force that pushes space apart appears to be a property of space itself. It is uniform. This means a cubic foot of empty void has just as much dark energy as a cubic foot of full space in a galaxy's core. 3. Primordial gas. Tenuous, ghostly wisps of hydrogen and helium, the raw, unprocessed leftovers from the Big Bang. 4. Void galaxies. A few lonely, isolated galaxies do exist in voids. These are often galactic backwaters, smaller, bluer, and less evolved than their counterparts in the dense filaments, as they have been starved of interactions and mergers.
The critical consequence of this low-density environment is the effect on gravity. Gravity is already the weakest fundamental force in nature. It requires enormous concentrated masses, planets, stars, galaxies, to show noticeable effects. In a void where mass is scarce, gravity's influence becomes almost negligible. In this environment, the other, more mysterious force in the universe becomes the undisputed king: dark energy. In dense regions of the universe, like in a galaxy cluster, gravity is strong. It creates a deep gravity well, pulling all the cluster members together. Here, gravity easily wins the tug-of-war against dark energy, and the cluster remains a bound object, no longer expanding. But inside a void, there is almost no mass. There is no deep gravity well. Gravity is too weak to put up a fight. Dark energy wins, decisively. As a result, voids expand faster than the rest of the universe. They are the bubbles in a loaf of bread rising, and they grow the most. This creates a self-reinforcing cycle. The more a void expands, the emptier it becomes, as its small amount of matter is spread over an ever larger volume, which in turn reduces its internal gravity even further, allowing dark energy to accelerate its expansion even more. This brings us to the physics of our situation. We are not just in a void, we are subject to its bizarre gravitational landscape. Scientists have confirmed this through careful observation. They've measured how galaxies near the edges of voids move compared to galaxies in denser regions. The galaxies at the edge are rushing away from the void's center faster than cosmic expansion alone would explain. Something is pushing them outward, or more accurately, something is pulling them outward. This is the concept of backwards gravity, or outflow. Think of a void as a deep, wide valley, surrounded on all sides by towering mountains. Gravity, which always pulls matter downhill toward a center of mass, has a strange effect here. Where is the mass? It's not in the valley, it's in the mountains. Therefore, the downhill direction of gravity is from the low-density valley toward the high-density mountains that form the void's walls. Everything in the valley, including us, is being gravitationally pulled outward toward the denser matter that forms the void's walls. The effect is measurable and significant. Galaxies inside the void are falling outward toward the denser walls. Our own galaxy, the Milky Way, is moving away from the center of our more local void at a staggering 600,000 miles per hour, or about 270 kilometers per second, driven by this very gravitational imbalance. The interior of a void becomes a strange place for physics. Even light is affected. When astronomers study the cosmic microwave background, the faint afterglow of the Big Bang, they notice that the light's path is altered by the structures it passes through. This is called the integrated Sachs-Wolf effect.
When a photon of light from the CMB enters a supervoid like ours, it's like it has to climb a slight gravitational hill because it's an underdensity, a lack of a gravity well. This costs the photon a tiny bit of energy, and it becomes slightly redshifted, cooler. While the photon is making its billion-year journey across the void itself is rapidly expanding, driven by dark energy. This expansion stretches and flattens the gravitational hill. When the photon finally leaves the void, it rolls down the other side. But because the hill is now flatter than when it entered, the photon doesn't regain all the energy it lost. The net result is that light passing through a massive and expanding void loses energy and appears slightly cooler, redder than it should. These cold spots in the CMB map line up perfectly with where we observe large voids today. This alignment is not a coincidence. It is physics. It is the direct, observational proof that voids are not just passive, empty spaces. They are active, expanding, and a dominant force in the universe's evolution. They are natural laboratories where dark energy reigns supreme, and we are lucky or unlucky enough to be living inside one. The cosmic web, a universe of foam. The universe is not a smooth soup of evenly distributed galaxies. When you zoom out to the largest possible scales, our cosmos resembles a three-dimensional spider's web, a sponge, or the neural network of a brain. Instead, it resembles Swiss cheese. Dense matter forms walls and filaments surrounding enormous hollow pockets. This vast foam-like architecture is called the cosmic web, and it represents the largest structure in nature. This structure is organized into a clear hierarchy, much like a biological organism. Nodes, at the intersections where multiple filaments meet, galaxy clusters concentrate. These are the cities of the universe, nodes of intense matter density, shining brilliantly with thousands of galaxies packed relatively closely together. These are the most massive, gravitationally bound objects in the cosmos, like the nearby Virgo cluster or the more distant Coma cluster. Filaments. Stretching between these nodes are the highways. These are long, twisting chains of dark matter and galaxy groups that can extend for hundreds of millions of light years. Our own Laniakea supercluster is, on a grander scale, part of such a filament. Walls. Filaments themselves can be organized into even larger flattened sheets, vast plains where galaxies gather in higher than average concentrations. The most famous is the Sloan Great Wall, a structure over 1.37 billion light-years long, discovered in 2003. And between all the filaments and walls lie the voids. These are the dark, empty bubbles that take up most of the volume of space while containing hardly any of the mass. This structure was not always obvious. For decades, astronomers photographed the sky and counted galaxies, but the true three-dimensional arrangement remained hidden. The universe looked like a flat, two-dimensional tapestry. The revolution came when scientists began measuring redshifts systematically in the 1970s and 1980s. The breakthrough came from the CFA Redshift Survey, led by Margaret Geller and John Huckra. In 1986, they presented their Slice of the Sky map. They had painstakingly measured the redshifts for all the galaxies in a narrow, wedge-shaped slice of the nearby universe. When they plotted the data with distance as the third dimension, the scientific community was stunned. The galaxies were not random. They were arranged in bubble-like structures, outlining vast spherical voids. Their data famously revealed a structure that resembled a stickman, a crude figure with galaxies forming the body and limbs, surrounding a vast emptiness. It was the first time humanity had seen the true, lumpy, foam-like architecture of the cosmos.
More surveys followed, each mapping deeper into space and revealing an increasingly intricate web. The Sloan Digital Sky Survey, also known as SDSS, which began in 2000, was a game-changer. It created spectacular 3D maps of over 1 million galaxies spanning billions of light-years. These maps show the cosmic web in stunning, undeniable detail. Filaments twist and branch like blood vessels. Voids appear as dark, near-spherical bubbles, some 500 million light-years across. The largest structures, like the Sloan Great Wall and the more recent Hercules Corona Borealis Great Wall, are so vast they challenge the cosmological principle all by themselves. On the opposite end of the spectrum, supervoids, like the Eridanus void, which we will return to, stretch 1.8 billion light-years wide, with even fewer galaxies than our own KBC void. Together, these features paint a picture of a universe organized on scales far larger than anyone predicted. Galaxies are not the fundamental building blocks. The web itself is the structure, with galaxies acting like dewdrops, just marking the intersections where the invisible matter happens to concentrate. Why does the universe organize this way? The answer reaches back to the beginning. Immediately after the Big Bang, the universe was not perfectly uniform. In the first fraction of a second, a period of exponential expansion called inflation took place. This violent expansion took the subatomic quantum world and magnified it to cosmic proportions. In the quantum realm, empty space is not empty. It's a roiling foam of virtual particles and energy fluctuations. Inflation took these tiny, random quantum fluctuations, ripples in the fabric of space-time itself, and stretched them from infinitesimal scales to cosmic scales. These fluctuations created tiny variations in density. Some regions were slightly denser than average, and others slightly less dense. These differences were minuscule, perhaps 1 part in 100,000, but gravity, acting over billions of years, amplifies even tiny advantages. The rich get richer. Denser regions had more gravity, so they pulled in more matter from their surroundings, making them denser still. This created a positive feedback loop. The poor get poorer. Less dense regions had less gravity, so they lost matter to their denser surroundings, becoming emptier. Over hundreds of millions of years, this process of gravitational collapse snowballed. The rich regions collapsed into the first stars, then galaxies, then clusters, which all drained along the paths of least resistance into the filaments. The poor regions, meanwhile, were drained of all their matter, expanding and merging to become the great voids. The cosmic web is essentially gravity's masterpiece, sculpted over 13.8 billion years, turning barely noticeable quantum ripples into the grandest architecture in existence. Today, this process has reached an extreme state. Voids occupy roughly 90% of the volume of space. The filaments and clusters, where almost all the light and matter reside, are compressed into the remaining 10%. This staggering imbalance defines the universe's character. We live not in a cosmos filled with galaxies, but in a cosmos of emptiness, punctuated by occasional concentrations of matter. The KBC void is just one bubble in this foam, but it happens to be our bubble, and that makes all the difference for what we observe and how we interpret the universe. Our address, a supercluster in a void. The Milky Way is not at the dead center of the KBC void, but it is close enough to matter. Measurements place our galaxy somewhere between 200 and 400 million light-years from the void's actual center. That might sound like a huge distance, but the void extends outward for 1 billion light-years in every direction from its center, making our offset relatively small. We sit well within the underdense region, surrounded by the void's low-density environment in all directions. This position is not random, and it has profound consequences for every observation we make. If we were located outside the void entirely, in one of the dense filaments, our measurements of the universe's expansion would look completely different. We would calculate a slower expansion rate, and the Hubble tension would simply not exist. Our larger cosmic neighborhood adds another fascinating and seemingly contradictory layer to this story. The Milky Way belongs to the local group, a small gravitationally bound collection of about 80 galaxies, including our giant neighbor Andromeda, which is on a collision course with us, and several smaller dwarf galaxies.
The local group itself sits on the outskirts of the Laniakea supercluster. Laniakea is a mind-bending structure identified in 2014 by a team led by Brent Tully at the University of Hawaii. It is a massive structure containing roughly 100,000 galaxies, including our own, spread across 520 million light-years. The name comes from Hawaiian and means immeasurable heaven, which is fitting given its scale. The most fascinating thing about Laniakea is how it was discovered. It was not seen as a distinct object. It was inferred by mapping the velocities of thousands of galaxies. Tully's team defined Laniakea not as a simple collection of matter, but as a cosmic watershed or a gravitational drainage basin. Think of a watershed on Earth where all the streams and rivers in a region flow downhill into a single large river valley. Laniakea is the cosmic equivalent. All 100,000 galaxies within its boundaries are flowing through expanding space toward a common center of gravity, a massive, unseen concentration of mass called the Great Attractor. The Great Attractor itself is a gravitational anomaly, a region of space about 250 million light-years away in the direction of the Centaurus cluster that is so massive it's pulling our entire local group and thousands of other galaxies toward it over 1.3 million miles per hour, or 600 kilometers per second. This leads to a mind-bending paradox, one that often confuses the entire discussion. How can we be part of a supercluster of 100,000 galaxies and also be inside a void defined by a lack of matter? The answer is a matter of scale. Laniakea is enormous by any normal standard. It is a vast continent of matter, yet the KBC void is so colossally vast, so much larger, that it can swallow entire superclusters and still be considered empty on average. Laniakea forms part of the sparse population of matter scattered through the void. It's one of the rare, significant concentrations in an otherwise barren expanse. The KBC void is defined by its lack of many superclusters, not a total absence of matter.
A structure of 100,000 galaxies, while huge to us, is just a small clump of debris inside a bubble 2 billion light-years wide. Our motion is a complex dance. We are being pulled by the great attractor within Laniakea. At the same time, the entire Laniakea structure is part of the outflow from the KBC void, being pulled outward by the even larger, more dense structures that form the void's walls. This makes our local patch of the universe far more dynamic and unusual than the calm, uniform cosmos that standard models assume. Our position inside the void also affects what we can see. When we look outward from inside the void, we see the shell of denser material surrounding us in all directions. That shell appears as a concentration of galaxy clusters and filaments at a specific distance range. This creates an observational bias. We are not sampling a random location in the universe. We are sampling from inside one of its most extreme and statistically unlikely features. And this bias is at the heart of the greatest crisis in physics. The Hubble tension is a crisis in cosmology. Every measurement you have ever heard about the universe's expansion rate might be wrong, not because scientists made mistakes, but because we're measuring from inside a cosmic hole that distorts the signal. This is the Hubble tension, the most profound and persistent crisis in modern physics. It is a deep, irreconcilable disagreement between the two most precise ways we have of measuring the Hubble constant, h sub 0, the number that tells us how fast space is expanding. This isn't a new debate. The Hubble War has been raging for 50 years. In the 1970s, Alan Sandage argued for a slow expansion, around 50, while Gerard de Vaucouleur argued for a fast expansion, around 100. Their error bars were so large they overlapped. We assumed better data would solve it. Instead, our data got impossibly good. The error bars shrank to almost nothing, and the two methods have settled on two different numbers. They are both right, and they are both wrong. This is the crisis. Method 1. The early universe. A prediction. The first method is an indirect measurement. It looks at the baby picture of the universe, the cosmic microwave background. This is the faint 2.725 Kelvin afterglow of the Big Bang, a wall of light emitted when the universe was just 380,000 years old. The Planck satellite, a multi-billion-dollar European Space Agency mission, spent years mapping this light in exquisite detail. The map isn't perfectly smooth. It has tiny hot and cold spots, or anisotropies, that vary by just 1 part in 100,000. These spots are the seeds of all future structure, the quantum fluctuations from inflation.
Scientists can analyze the size of these spots, specifically the acoustic peaks in the CMB power spectrum. These peaks correspond to baryon acoustic oscillations, which are essentially the sound waves that rippled through the hot, dense plasma of the early universe. The physics of this plasma is so well understood that scientists can calculate exactly how far these sound waves could travel before the universe cooled and froze them in place. This gives us a standard ruler. We know exactly how big these spots were, about 490,000 light years across at the time. By measuring how big they appear to us on the sky today, about 1 degree, we can calculate the precise geometry of the universe and how much it has expanded. But this isn't a direct measurement of the current expansion. Instead, scientists feed this incredibly precise Planck data, the spot sizes, the temperatures, the density of matter, and dark energy, into our best model of the cosmos, the lambda-cold dark matter model. This is the standard model of cosmology. This model, this cosmic recipe, then runs the clock forward 13.8 billion years and predicts what the expansion rate must be today. That prediction is rock solid. HO equals 67.4 plus or minus 0.5 kilometers per second per megaparsec. For every 3.3 million light years of distance, space expands by 67.4 kilometers per second. This number is incredibly precise and has been confirmed by other early universe methods like BAO mapping in distant galaxies. Method 2, the late universe, a measurement. This second method is a direct measurement. It ignores the early universe entirely and looks at objects in the nearby or late universe from today back to a few billion years and measures their distance and speed. This method relies on the cosmic distance ladder. Step 1. Parallax. For stars very close to us in our own Milky Way, we can measure their distance directly using simple geometry. By observing how a star's position appears to shift against the background as the Earth orbits the Sun, we can triangulate its distance. This is the bedrock, the first rung of the ladder, made hyper-precise by the Gaia Space Observatory. Step 2. Cepheid variables. These are the standard candles of the cosmos, special stars that pulse in brightness. Their discovery is a story of its own. In the early 1900s, Henrietta Swan Leavitt, a human computer at Harvard, was cataloging stars. She noticed that for a class of stars called Cepheids, the speed of their pulse, their period, was directly related to their true brightness, their luminosity. A star that pulsed faster was intrinsically brighter. This was a monumental discovery. It means that by simply timing a Cepheid's pulse, we know how bright it really is. By comparing its true brightness to its apparent brightness in the sky, which follows the inverse square law, we can calculate its distance with incredible precision. This gets us to nearby galaxies. Step 3. Type 1a supernovae. These are the standard bombs of the cosmos. They are the thermonuclear explosions of white dwarf stars. A white dwarf, the dead core of a sun-like star in a binary system, can siphon material, hydrogen and helium, from its companion star. As it feeds, its mass grows. When it reaches a precise, critical mass, the Chandrasekhar limit, about 1.4 times the mass of our sun, the pressure and temperature in its core becomes so high that it ignites runaway carbon fusion. The entire star detonates in a matter of seconds. Because they all explode at exactly the same mass, they all reach exactly the same peak brightness. These explosions are so blindingly bright, they can outshine their entire galaxy and be seen billions of light years away. A team led by Nobel laureate Adam Rees, called SHOES, supernovae HO for the equation of state of dark energy, uses the Hubble Space Telescope and now the James Webb Telescope to find galaxies that conveniently contain both Cepheids and a Type 1a supernova. They use the Cepheids, step 2, to get a rock-solid distance to that galaxy, which calibrates the exact brightness of the supernova. Once calibrated, they can look for other, much more distant Type 1a supernovae, and by measuring their apparent brightness, find the distance to them. By comparing the distance of these supernovae to their redshift, their speed, they can directly measure the current expansion rate. Their measurement is just as precise and just as unwavering as Planck's, but it gives a completely different number. HO equals 73.3 plus or minus 1 kilometers per second per megaparsec. The crisis, 67.4 versus 73.3. The difference is 9%. The error bars on these two multi-billion-dollar Nobel Prize-winning experiments do not overlap. This isn't a small disagreement. It's a 5 sigma tension. In particle physics, 5 sigma is the threshold for a discovery. It means there is less than a 1 in 3.5 million chance that this discrepancy is a random statistical fluke.
Something is fundamentally broken. Is our early universe measurement, Planck, wrong? Unlikely. The data is too good. Is our late universe measurement, supernovae, wrong? Unlikely. The SHOES team has defended its data against all criticism. Are both correct? If so, it means the LCDM model itself, our entire understanding of cosmic evolution, the bridge that connects the early and late universe, is wrong. For a decade, this has been the central agonizing problem in physics. Theorists have proposed exotic new physics to solve it. New forms of early dark energy, new phantom particles, modifications to Einstein's theory of gravity. None have worked cleanly. The KBC void provides a fourth, radical, and stunningly simple solution. Both measurements are correct, but they are measuring different things. The Planck measurement of 67.4 kilometers per second per megaparsec is the true global average expansion rate of the entire universe. The supernova measurement of 73.3 kilometers per second per megaparsec is the local expansion rate measured from inside the bubble. The KBC void's gravitational outflow, the backwards gravity pulling us out, adds an extra kick to all the nearby galaxies we are measuring. This bulk flow, driven by the void, adds a few kilometers per second per megaparsec to the local measurement. 67.4 true global average expansion plus approximately 6 local void outflow equals approximately 73.4, what we locally measure. The Hubble tension vanishes. The crisis is resolved. But it comes at a cost. We must accept that our location in the universe is special and that our model of cosmology is collapsing, not because the physics is wrong, but because we've been applying it from a biased, privileged, and statistically impossible perspective. The end of the cosmological principle. The KBC void is not just a scientific problem, it's a philosophical one. Its existence represents a fundamental challenge to our understanding of our place in the cosmos, an idea that has been the bedrock of physics for a century. This challenge is to the cosmological principle. As we've discussed, this principle states that the universe is homogeneous and isotropic on large scales. In simple terms, our location is not special. This idea is the final step in a 500-year-long great demotion of humanity. Aristotle and Ptolemy placed Earth at the center of the universe. We were the special, unmoving point around which all of creation, the sun, the planets, the firmament of stars, revolved. Nicholas Copernicus and later Galileo Galilei shattered this. In 1543, he published his work De Revolutionibus Orbium Caelestiums, which demoted Earth. It was not the center, it was just another planet revolving around the sun. This was a profound philosophical shock. Harlow Shapley delivered the next blow in the 1920s. By mapping the locations of globular clusters, ancient balls of stars, in our own galaxy,
He showed that our sun was not at the center of the Milky Way. We were in the suburbs, a small, unremarkable star in the galactic outskirts. Edwin Hubble delivered the final demotion. In 1924, by observing Cepheid variable stars in the Andromeda Nebula, he proved it was not a cloud of gas within our own galaxy. It was an island universe, another entire galaxy, just like our own, millions of light years away. This discovery expanded our reality from one galaxy to billions. The cosmological principle was the ultimate expression of this trend. It says that not only is Earth not at the center, and the Sun not at the center, and the Milky Way not at the center, but that there is no center. Every location is equivalent. This assumption is not just a philosophical preference. It is baked into the mathematics of Einstein's equations of general relativity. The Friedmann-Lemaitre-Robertson-Walker metric, the set of equations we use to describe our expanding universe, only works if we assume the universe is homogeneous and isotropic. The principle makes the math possible. It allows us to apply the laws of physics we learn on Earth to the entire cosmos. The KBC void threatens to shatter this. If we live inside a 2 billion light-year wide bubble that is 20% emptier than average, our location is unusual. It's not just unusual, it's, as we've seen, statistically impossible according to the very models built on the cosmological principle. The 10 sigma rarity suggests we are in a place that shouldn't exist. This forces us into a deeply uncomfortable choice. Which is more likely? 1. We are a statistical miracle? We just happen to live in the 1 in trillion place that has these properties, and it just happens to be a place that perfectly and coincidentally resolves the single biggest paradox in modern physics, the Hubble tension? Many scientists find this coincidence deeply suspicious.
2. The standard model, the LCDM, is wrong. The model that predicts such voids are rare must be flawed. Perhaps structure formation works differently, and these voids are actually common. But if that's true, it requires rewriting our understanding of dark matter or gravity. 3. The cosmological principle is simply wrong. The universe is not homogeneous on these scales. Our location is special, and our physics is therefore local, not universal. This last possibility is the most terrifying for physicists. It means we can't trust that our measurements reflect the universe as a whole. It suggests we live in a Hubble bubble, and our cosmological measurements are only valid inside this bubble. The laws of physics might not be as universal as we thought. The KBC void forces us to choose between an uncomfortable coincidence, we are statistical miracles, or an uncomfortable truth, our foundational models are broken. Our 1.4 million mile per hour plunge, the proof of the push. The outflow from the void isn't just a theory to fix the Hubble tension. We have direct, independent proof that we are being pushed. That proof is written across the entire sky. It is the CMB dipole. As we discussed, the Planck satellite mapped the cosmic microwave background, the 2.725 Kelvin afterglow of the Big Bang. But the very first thing Planck and its predecessors, like COBE and WEMAP, had to do was to subtract our own motion.
Before you can see the tiny primordial 1 in 100,000 fluctuations, you have to account for a massive 1 in 1,000 signal that drowns them out. This signal is a dipole. The sky is slightly hotter by about 3.3 millikelvin in one direction and slightly cooler in the opposite direction. This is not a primordial feature. This is a simple Doppler effect. It is the wind we feel as our entire galaxy, our entire local group, plummets through the cosmos. In the direction we are moving, toward the constellation Leo, the ancient light of the CMB is compressed and we see it as slightly blue-shifted, or hotter. In the direction we are moving away from, the light is stretched and we see it as red-shifted, or cooler. This dipole is a direct, unambiguous measurement of our peculiar velocity, our motion relative to the rest frame of the entire observable universe. This speed this dipole implies is staggering. 627 plus or minus 22 kilometers per second. That is 1.4 million miles per hour. For decades, astronomers have tried to figure out why we are moving so fast and what is pulling us. By mapping the galaxies around us, they've built a gravitational budget. 1. A small pull from the Virgo cluster, the nearest large galaxy cluster. 2. A massive pull from the Great Attractor, the heart of our Laniakea supercluster. 3. A more distant pull from the Shapley supercluster, an even larger concentration of mass downstream from the Great Attractor. But for years, these pulls didn't add up. They couldn't fully account for our 1.4 million mile per hour velocity. There was a missing component. The KBC void provides the missing piece. It's not just a pull from Leo that's dragging us. It's also a push from the opposite direction. This push, of course, is the backwards gravity of the void. It's the lack of a gravitational pull from the vast empty region behind us, which makes the pulls from the Great Attractor and Shapley all the more effective. It's the valley we are falling out of. Our high speed through space is itself one of the strongest pieces of evidence for the void. If we lived in a region with average density, our peculiar velocity would be much smaller. The fact that we are moving so fast indicates powerful large-scale gravitational gradients in our vicinity, exactly what you would expect from living inside a massive cosmic valley. The universe may be lying to us about its expansion rate, but it cannot hide the fact that we are racing through it at incredible speed. The CMB dipole is the receipt for the void's gravitational push.
The origin of these vast empty regions, these billion light-year-wide holes, reaches back to the universe's first moments. The KBC void is not just a structure, it is a fossil. It is a relic from the first 10 to the negative 35 seconds after the Big Bang. In the standard model of cosmology, the universe began with a bang, but immediately after, it underwent a period of exponential, faster-than-light expansion called cosmic inflation. This idea was proposed in the 1980s by physicists like Alan Guth to solve several deep problems with the Big Bang model, like why the universe is so flat and so uniform. During this infinitesimal slice of a second, the observable universe swelled from a size smaller than a proton to the size of a marble. This violent expansion took the subatomic quantum world and magnified it to cosmic proportions. In the quantum realm, empty space is not empty. It is a roiling, chaotic quantum foam of virtual particles and energy fields popping in and out of existence, governed by the Heisenberg uncertainty principle. This means that at any given instant,
The vacuum is not perfectly uniform. It has tiny, random fluctuations in energy. Inflation took these tiny, random energy fluctuations and stretched them. A region that for a split second had slightly more energy, a positive fluctuation, was stretched to become a denser region in the new large-scale universe. A region that had slightly less energy, a negative fluctuation, was stretched to become an underdense region. These were the seeds. The density differences were minuscule, 1 part in 10 to the 100,000. But gravity, acting over 13.8 billion years, amplified them relentlessly. The denser regions pulled in more matter, collapsing to form the filaments and clusters of the cosmic web. The underdense regions lost their matter to their neighbors, expanding and emptying out to become the voids. The cosmic desert we inhabit today traces its origins back to a single, random, negative quantum fluctuation that occurred before atoms, light, or matter as we know it even existed. Our location in the cosmos is the result of a quantum roll of the dice 13.8 billion years ago. This origin story is precisely what makes the KBC void's 10 sigma improbability so troubling. Standard inflation models predict a scale-invariant spectrum of fluctuations, meaning they should be roughly the same at all sizes. This model is very good at producing small voids. It is very bad at producing 2 billion light-year-wide supervoids. To get a KBC void, you need a primordial quantum seed that was already huge and poor, underdense. This is statistically possible in the same way that flipping a coin and getting heads 500 times in a row is possible. It's so unlikely that if you saw it, you wouldn't assume you were lucky. You'd assume the coin was weighted. The KBC void is that weighted coin. It's a fossil from the first picosecond of time, and it's telling us our model of inflation, our very origin story, might be incomplete. A universe 90% empty. The galactic backwaters. The scale of these empty regions dwarfs human imagination. When you picture the universe, you probably imagine a sky full of stars and galaxies, but the reality is the opposite. The universe is overwhelmingly empty. As the cosmic web reveals, voids occupy roughly 90% of the total volume of space. Galaxies and galaxy clusters, all the matter, all the light, all the stuff, are crowded into the remaining 10% of volume, packed into the thin, glowing filaments and nodes. This is not just empty space in the sense of the vacuum between stars. It is empty in the sense that entire regions, hundreds of millions of light years across, contain almost no galaxies at all. If you could travel in a spaceship at the speed of light, you could fly for tens of millions of years through a typical void without encountering a single major galaxy. The isolation would be near absolute. This distribution creates a lopsided universe. Most of the matter concentrates in a small fraction of the volume. Filaments and nodes, 10% of volume, are crowded, chaotic, and fast-paced. Galaxies interact frequently, colliding and merging. This galactic harassment and cannibalism is a primary driver of evolution, triggering bursts of star formation, feeding supermassive black holes, and stripping galaxies of their star-forming gas. Voids, 90% of volume,
are quiet, isolated, and underdeveloped. The few galaxies that do exist in voids are unique. These void galaxies are galactic orphans. They are galaxy backwaters, evolving in profound loneliness. Because they rarely interact or merge with other galaxies, their evolution is slow, peaceful, and stunted.
Astronomers observing them find they are very different from field galaxies. They are typically smaller and dimmer, more dwarf galaxies. They are bluer, indicating they are still actively, if slowly, forming new stars. In contrast, cluster galaxies have their star formation quenched and are red and dead. They are gassier, often containing large, pristine reservoirs of the primordial hydrogen gas that they have failed to convert into stars over 13.8 billion years. Life inside a void galaxy would be strange. The night sky would be profoundly dark. In the Milky Way, we are surrounded by our local group. Andromeda is a visible smudge, and the Milky Way's band is a river of light. In a true void galaxy, the sky might be almost completely black, with no other galaxies visible to the naked eye. It would be a lonely, isolated existence. This 90% void fraction is not static, it is growing. As dark energy accelerates cosmic expansion, it expands the voids fastest of all. The voids are in effect eating the filaments. Over billions of years, the cosmic web will be stretched and torn apart, leaving the galaxy clusters as lonely, isolated islands in an ever-expanding ocean of emptiness. The universe's destiny to become increasingly hollow. A crisis of gravity. Does MOND solve the void? The KBC void's impossibility has become ammunition for a fringe group of scientists who believe the standard model is not just incomplete, but fundamentally wrong. They argue that the problem isn't dark matter or rare statistics. The problem is gravity itself. The standard theory of gravity is Einstein's general relativity. It has been the bedrock of physics for a century, passing every experimental test thrown at it. We've heard its black hole mergers with LIGO and seen its lensing effects with Hubble. It is a triumph. But to make it work on cosmic scales, we've had to invent two fudge factors that we cannot see or explain. Dark matter, the invisible mass holding galaxies together, and dark energy, the mysterious force pushing space apart. Together, they make up 95% of the universe. The most prominent alternative theory is called MOND, Modified Newtonian Dynamics. Proposed in the 1980s by Israeli physicist Mordechai Milgram, MOND is a radical idea. It suggests that there is no dark matter. Instead, our understanding of gravity is wrong. Milgram proposed that gravity behaves differently when accelerations are extremely small, as they are in the outskirts of galaxies or on cosmic scales. In these low acceleration regimes, MOND suggests gravity becomes stronger than Einstein's or Newton's theories predict. This was originally proposed to explain a specific problem: galaxy rotation curves. In the 1970s, Vera Rubin observed that stars in the outskirts of galaxies were rotating just as fast as stars in the center. This defied Newton's laws. The outer stars should have been moving slower. This missing mass was the primary evidence for dark matter. MOND's stronger gravity solves this problem perfectly, without any dark matter at all. But it has a fascinating side effect related to voids.
If gravity is stronger on large scales, it makes structure formation more efficient. Denser regions collapse faster and become denser. Underdense regions are emptied out more effectively, becoming deeper. In a Mond universe, computer simulations naturally produce voids as large and deep as the KBC void. The 10 sigma improbability vanishes. The void becomes an expected feature of a universe with modified gravity. This is an attractive solution. It also naturally explains the high-velocity bulk flows we observe, as stronger gravity would create stronger gravitational valleys and mountains. However, Mond is not a silver bullet. While it succeeds brilliantly on galaxy scales, it fails spectacularly on larger cosmological scales. 1. It cannot explain the bullet cluster. This is a smoking gun observation of two galaxy clusters that have collided. We see the hot gas, normal matter, in the middle, while gravitational lensing shows the mass, dark matter, has passed right through. Mond cannot explain this separation. 2. It cannot explain the cosmic microwave background. The precise pattern of the acoustic peaks in the Planck data is a perfect fit for a universe with 85% dark matter and 15% normal matter. Mond cannot reproduce these peaks. For these reasons, Mond remains a compelling but deeply flawed alternative. But the KBC void's existence continues to provide fuel for those who believe that our understanding of gravity, the most fundamental force of all, is in need of a revolution.
An age crisis. The stars older than time. The KBC void's existence threatens our calculations of the most fundamental number of all, the age of the universe. As we've seen, the Hubble tension is a battle between two numbers, 67.4 and 73.3. This isn't just an abstract velocity, it's a cosmic clock. The Hubble constant h0 is inversely related to the age of the universe. Age is approximately 1 divided by h0. A faster expansion means the universe reached its current size in less time. Let's look at the two clocks derived from the two tensions. Planck's clock, h0 equals 67.4. This slower, early universe expansion rate gives us an age of 13.8 billion years. This is the number you see in all the textbooks. Schu's clock, h0 equals 73.3, this faster, late universe expansion rate implies the universe reached its current size much more quickly. This gives a much younger universe, aged only 12.7 billion years. This 1.1 billion year difference creates an immediate and logical impossibility. It is a second, independent crisis. We observe stars in our own galaxy that appear to be older than the young universe. The most famous example is HD 140283, nicknamed the Methuselah star. It's an ancient metal-poor star in our galaxy's halo. Being metal-poor means it formed early, before generations of supernovae had enriched the cosmos with heavy elements. Based on our best, most modern models of stellar evolution, its age is estimated to be around 14.27 billion years, with a large error bar of about 0.8 billion years. Even at the low end of its error bar, it's at best 13.5 billion years old. A more robust example are the globular clusters. These are ancient, dense spheres of stars that all formed at the same time. We can age them very precisely by looking at their main sequence turnoff, the point where stars of a certain mass are just beginning to die. These clusters, like Messier 92, consistently date to 12.5
to 13 billion years old. You simply cannot fit 13-billion-year-old stars into a 12.7 billion-year-old universe. It is a paradox. This age crisis forces a terrible choice. Is our understanding of stellar evolution, how stars age and die, completely wrong? Is our local measurement of the universe's expansion, the 73.3 number, correct, meaning the universe is young and our stars are impossible? Or is the early universe measurement, the 67.4 number, correct? Once again, the KBC void rides to the rescue. It provides a clean, elegant solution. The KBC void hypothesis states that the 13.8 billion year age is correct. The 67.4 number is the true global expansion rate. Our 13 billion year old stars fit comfortably inside this timeline. The younger 12.7 billion year age is a phantom number. It's a fiction, a cosmic illusion, an incorrect answer derived from a locally polluted measurement. The 73.3 H0 value isn't the true expansion rate of the universe. It's just the local expansion rate, which has been artificially inflated by the void's outflow. Once again, accepting our special location saves the rest of our physics. It resolves the Hubble tension and it resolves the age crisis. It is the single key that unlocks both of cosmology's biggest paradoxes.
This discovery led to a wave of wild, exotic explanations. The most famous, proposed by physicist Laura Mersini-Houghton, was that this was a cosmic bruise. She theorized that our universe is just one bubble in a larger multiverse of other bubble universes. The cold spot, she argued, was a literal scar, a leftover imprint from a collision between our universe and another bubble universe in the distant past. However, there was a more mundane but still bizarre explanation rooted in the KBC void concept. What if the cold spot was not a primordial feature from the Big Bang, but a foreground effect? What if, as we theorized with the ISW effect, the ancient light of the CMB was passing through a colossal supervoid on its way to us? Such a void would stretch the light and make it appear cold. Astronomers pointed their telescopes in that direction, and sure enough, they found one, the Eridanus supervoid. This was a major discovery. It seemed to solve the problem, but a new mystery emerged. When astronomers modeled the void, they found it wasn't deep or large enough to explain the entire coldness of the cold spot. It only accounts for about 20 to 30% of the temperature drop. This has left the cold spot as an unresolved mystery. Is it a combination of a supervoid and a rare primordial cold fluctuation? Is it a sign that our understanding of the ISW effect is wrong? Or was Mersini-Houghton right? The key takeaway for our story is this. The fact that two such statistically impossible supervoids have been found, KBC and Eridanus, makes the "we are just lucky" argument even weaker. If these 10 sigma rarity objects are found twice in the limited part of the universe we can survey, maybe our model is wrong. Maybe these supervoids are in fact common. But if they are common, it means our standard LCDM model of structure formation is fundamentally broken. The future, a great and lonely emptiness.
The KBC void does more than just skew our measurements. It gives us a chilling preview of the ultimate fate of the entire cosmos. The dominant force in our universe is now dark energy. It is accelerating the expansion of the universe. This acceleration is most powerful in the voids. As we've seen, this means the voids will grow faster and faster, expanding and merging. The filaments of the cosmic web will be stretched thin, and then, one by one, they will be torn apart. This will lead to a future of cosmic isolation. Let's fast forward. In 4 to 5 billion years, our Milky Way galaxy will collide and merge with the Andromeda galaxy, forming a single giant elliptical galaxy, Milkomeda. In 100 billion years, the accelerating expansion of space will have pushed all galaxies outside our own local group, which will then be Milkomeda, over our cosmic horizon. They will be receding from us faster than the speed of light. Their light will be stretched into invisibility. They will be gone forever.
Cosmology, as a science, will die. A future civilization in this lonely island universe will look out at their sky and conclude, logically, that they live in a single, static, empty, unchanging cosmos. They will have no way of knowing about the Big Bang. They will have no way of knowing about cosmic expansion, dark energy, or the billions of other galaxies that once existed. They will be living in a cosmic bubble of their own, but this one will be a bubble of ignorance imposed by the very laws of physics. The KBC void we live in today is a microcosm of this future. It is a region where the isolation, the low density, and the dark energy-driven emptiness that will one day define the entire universe are already dominant. We are getting a sneak peek at the end of all things. Conclusion: the collapse. We are inside a cosmic hole 2 billion light years wide. This is not a metaphor. This is not science fiction. This is the most likely and most logical conclusion from the data. The KBC void is real. Its effects are measurable. Its backwards gravity outflow, which we can measure as our 1.4 million mile per hour motion through space, is the key. This one single uncomfortable idea that our location is a 10 sigma statistical improbability resolves everything. It resolves the Hubble tension, explaining why Planck's early measurement of 67.3 is the true global number, while our late measurement of 73.3 is a local number, polluted by the void's outflow. It resolves the age crisis, confirming the universe is 13.8 billion years old, giving our 13 billion-year-old stars plenty of time to exist. And it explains why the universe appears lumpier with voids like Eridanus and KBC than our models predict. The collapse in the title is twofold. It is the literal collapse of matter out of our void, the gravitational outflow that defines our motion, but it is also the collapse of our model, the beautiful, simple 20th century idea of the cosmological principle, the idea that we are average, is dead. We are not average. We are special. We are cosmic castaways, adrift in a bubble of emptiness, measuring a universe that is not what it seems. And for the first time, we are beginning to understand the true shape of our cosmic prison.